research in clustering, because either you work at some entity, like a private corporation or something, where you actually access data, because you can't publish it. Right? Usually the data is proprietary. Or you work in academia or some kind of place where you do want to use public sources, and then you can no longer find good data sets because all you do is firewalls. So it is tough, and that makes it, finding good data is, and this is not just from the clustering, but all kinds of data mining research, finding good data to play with is very, very hard. So while I prevented you from using the UCI database, it has been very valuable over the years for people. Just that at this point, I think it's outlived its value. It's been optimized so heavily against that it's not, it's nice to, it would be nice to get some diversity. So what you're doing is kind of a social service for the community at large as well as doing this assignment. The data sets you find are going to be, something that other people hopefully will use. They can cite this class and sort that. Yes?
All of a sudden, data set elsewhere, but not in UCI, but organic data is found that it was stored in UCI.
What do you mean it's already in UCI?
It was actually a data set that was already in UCI.
Yeah.
But I found it elsewhere.
Did you check?
But later on, when I was checking UCI data set, I found it was already.
Well, I would suggest you look more. Okay. So that's much for administrative questions. And again, the thing is due next Tuesday. I will set up an upload mechanism. Basically, you just, I guess, you're going to upload a document, and you're going to put the link to your thing on the page on your website. Okay. So yeah, please don't. It's going to be hard to submit something handwritten. We don't even try something PDF. Just get some upload PDF, whether you did it in later or whatever. All right. The first thing I want to talk about today is k-means in game. I want to go back to it because I think there are some interesting features of the algorithm that lend itself to more generalizations. And we'll see some of these later on, but I want to sort of mention some of them now. I alluded to them briefly last time, but I didn't go into detail. So if you remember the k-means problem, right? Given some subset of this is a notation for Euclidean space of dimension d. So Euclidean is L2 distance, and d dimension. Yeah, the dimensionality doesn't matter so much. Some finite set. Find the partition with means C1 through Ck such that we minimize the sum over all points of the min over all Ci. This is the way to say the same thing. What I'm saying is that take every point, find its nearest cluster center, which in fact is the cluster you will assign it to, measures distance squared, minimizes gigantic sum. Right? This is the k-means objective function. And we have seen that there are algorithms that will produce good solutions to this problem. We've also seen this canonical k-means algorithm. Right? So it's distinguished the problem. Which is also called, Lloyd's algorithm. Maybe a better way to refer to it, so we don't confuse the things. Which basically says, initialize C1 through Ck in some fashion. Step 2 is assign each point to nearest cluster. And step 3 is let Ck be set of points of xi assigned to Ci, compute Ci nu is equal to the sum of all the xi divided by the size of the system. Right? And these are, of course, are the two key steps. And so then you say, go to step 2 if change happens. Right? If your clusters actually move, and again, you can think of some tolerance parameter. You go back. And each of these steps, these two steps, had an important justification. Right? What is the justification for step 2? Why was this an okay thing to do? Because if I tell you what the cluster centers are, then the best thing you can do for a point is to assign to its nearest cluster. Why is this the best thing to do? What is this justified by? Sorry? Is that the root word? So we're saying in step 3, if we take the mean of the points to be the cluster center, it does what? Go ahead. Why is that a good thing to pick that?
It will be almost at the equal distance for all the points.
No.
But it should minimize the overall count of edge distances.
So in other words, if I give you the cluster centers, the best you can do is assign each point to its nearest cluster center. If I give you the clusters, the best way you can get the centers is to pick the mean. This is what's called, by the way, this is a bit of a digression, but this is what's called an alternating optimization. So this is a very common setting in many problems in sort of slightly non-convex optimization, where your basic setup is I have some function, and it's a function of 2 parameters, and my goal is to minimize this function. Okay? And this function is non-convex, so I don't really have any hope of finding the optimal solution to this problem easily. But I do know that for any fixed x hat, this problem over y is convex. And for any fixed y hat is convex. Okay? Suppose I have a setting like this, and there are surprisingly many settings where you see something like this. But if I knew one of the parameters, I can optimize over the other. So this obviously lends itself to this kind of alternating optimization. Guess some value of x, use that to find y. Use that value of y to find x. Okay, so this general framework, which is very, very common, is called an alternating optimization, and k-means is a classic example of this. Because if you knew the cluster centers, we know what to do. If you knew the clusters themselves, you know what to do. We just don't know what to do for both the same. Okay? So as a heuristic, for a problem you're looking at, this is a very good heuristic. There are certain cases under which you can actually prove optimality. For example, one example where this actually can get the optimal solution is if I have 2 convex sets or polytopes in high dimensions, and I want to find the closest pair between them. This is tricky to do, but it falls into this framework where you now say, given a point here, I can find the closest point there. Given a point here, I can find the closest point here. And soon you end up with the closest pair. Okay. Again, you have to prove that this converges at a reasonable rate and so on and so forth, but you can actually find the optimal solution. So there's some cases where you actually do get the optimal answer. There are mostly cases where you don't, but it's a very good heuristic. And you see this, you'll see this showing up all over the place. Okay, so it's good to recognize this. Yes?
But k-means, when do we stop and do we keep measuring the distance between the
when the change is very, very small. So there's some threshold, some heuristically defined threshold, right? The problem is that when you're dealing with points in smooth space like L2, you can no longer, well, the cost keeps decreasing. Right, so the number of partitions is bounded. Like it's this partition number of n into k parts. And so you will never cycle. Because the cost keeps decreasing, if once you hit a partition and you move down below it, you'll never get back to that partition because that would be an increase in cost. You can never increase the cost. So if you think of this gigantic list of partitions, you're just sort of walking down the list. And eventually you stop. Because eventually it's not very comforting. This is why you put a threshold. It's a very long game. Okay, so this is an example of an alternating optimization. But it's also an example, in particular for clustering, of something very nice. So we said that these two steps are justified because you can prove that for any fixed one, you can optimize the other and it's convex, so you know the solution. But this also is an example of this nice property, right? So this is what we've been calling the Voronoi property. Right? That for a clustering problem, it admits the Voronoi property if once you choose these centers, the right thing to do is to assign a point to its nearest cluster center. And this property is this kind of mean property, the property that the mean optimizes the cost function you're trying to look at for a particular problem. Right? This is not true, for example, for k median. Right? The mean is not the thing. Something else is the median is the thing that optimizes. In fact, you could define the k median algorithm that we talked about briefly in the same fashion, where instead of this step, you find that one median. It's the same thing. It's a thing that optimizes that one. But for means, you need to do the centroid is much easier to do. It turns out that there are other formulations where this is no longer true. But these two steps are true. And for those problems, you can again use this algorithm. And so the reason I'm saying this is that it's important to realize, what parts of this algorithm need what things. It might seem like I need Euclidean distance for this, because I'm going to prove this using Euclidean distance and squares, or I differentiate things. It turns out you don't need that. And that's very interesting because it allows you to generalize this algorithm to other spaces as well. Right? So it cuts down on this clutter of algorithms that we need to have. And this is what I was referring to last time as these so-called Bregman divergences. So this is so let me quickly define a Bregman divergence in a somewhat obscure way, and I'll try to make it more picturesque. So just be patient for a minute. So think of P as some kind of convex function. For now, let's keep it even simpler. And let's assume it's from Rd to R. So some kind of scalar function over Rd. Okay, you can think of this as a function that takes a point Rd and lifts it up one dimension higher. And let's assume it's convex. This is very important. In fact, we'll assume it's strictly convex. So there's no flat parts. Okay. I'm going to take this function and construct a distance from it. Okay, and the distance I'm going to construct. My phone stops making noises. Is this. So I'm going to find the distance. It's parameterized by P. Okay. From, let's say, x to going to be an asymmetric function. Okay. It's not even going to be symmetric. So I'm going to put it in this form. So you can actually put it like this. This way you can see this. Is equal to this weird function. So before you even try to parse this horrible expression, let me draw a picture. These pictures are so much more fun. So what is that expression telling us? It's got this, so first of all, let me just parse the syntax, right? So phi of x, which is a scalar, minus this quantity, which is phi of y, again a scalar, plus the inner product, the dot product of the gradient of phi. So again, if you're like me and you hate thinking in higher dimensions, the derivative of phi times x minus 1, dot x minus y, right? Because these are two vectors. So what does this mean? Well, actually it just means the thing you would expect to mean. This is the Taylor expansion of phi of x, the first order Taylor expansion of phi of x at y. It's saying if I don't know what phi of x is, and I want to approximate it by the value I do know at phi of y, the first order Taylor expansion is just take a straight line approximation. Right? I have this point, I have the first order term, I say, okay, I'm going to approximate this curve by this straight line. How bad is my approximation? That's the value. This is the true value phi of x. This is the value I'm getting from my approximation. And now you see why this convexity is important. X, I could not guarantee this was always above that. And this number would not always be positive, but in fact it's always positive. Because of convexity. In fact, you can show that this big expression here, again by Taylor expansion principles, is some kind of Hessian, some kind of second order term.
So,
yeah.
So P is class of all convex functions, or there's specific class of functions?
So for every convex function you give me, I will wrap it up in this little package and give you back a distance.
Okay. Any convex function?
Yeah.
Okay.
Well, yeah, there's some other minor technical additions, but basically as well. In particular, let us set the Euclidean distance with a length squared. Okay? If you plug this expression in here, okay, note that the derivative of this function was the derivative of this. This is basically x, if I'm not mistaken, the grad. Okay, because basically it's, or maybe it's 2x. Maybe I have to put a half here. But basically, because every coefficient, this expression is sum of xi squared. You take the partial derivatives with respect to each coordinate, you're going to get that coordinate back. Right? And so the derivative, which is a vector, is going to be x itself. If you plug it in up there, what do you get? You get x squared minus y squared plus dot product of x comma x minus y, right? Which is equal to x squared minus y squared, not to be careful, minus x squared, minus right? What are two somewhat, didn't I? Yeah, 2. Plus 2xy
Minus. Right.
Oh yeah, yeah. I'm sorry. This was 2y. Yeah, minus. Right. Okay. Simplify this. You get. So if I take the generating convex function phi of x equal to length of x squared and plug it into my distance generator, what I get is the square of the Euclidean distance, which is kind of nice. But it turns out what is cooler is that you can put in other kinds of convex functions, get other kinds of strange beasts that we see out in the wild but didn't know were related. For example, there's a very well-known distance that comes from information theory called the Kullback-Leibler divergence, also known as the relative entropy, also known as the cross entropy, and who knows what else it's called. So it's defined as Kullback-Leibler divergence between two distributions P and Q. Let's say they're defined finitely over some finite set of n objects. So there's P1 through Pn and Q1 through Qn. is equal to this summation, pi log pi over qi. Now, first of all, it's not obvious this number. It's clear it's asymmetric. It's not clear what you can do with it. But it turns out that this is exactly equal to p comma q, or p equal to sigma xi log. So if you take that convex function, which is convex, and then plug it into this definition, you recover the Kullback divergence. So in some sense, the Euclidean distance squared and that distance are related. And there's a whole bunch of other ones that show up in machine learning. They're very cool. And so they're related, and what's nice is that all of these divergences, called the Bregman divergences, satisfy these properties. Namely, they satisfy the borderline property, that the closest, if you have a point and you want to find its closest. So if you define now your cost function, instead of that, you define it as now sigma x belonging to x min over ci. And you have to be a little bit careful here because the direction matters. So one way to write this is that the Bregman divergence x comma ci. So from point 2 cluster. Okay. And that's a clustering you want to optimize. So you have a bunch of distributions and you want to optimize, you want to cluster them with respect to the Kullback divergence. You don't need a brand new algorithm because it turns out that this distance function, this property here, satisfies both the nearest neighbor and not obvious at all. In other words, the point that minimizes this sum is in fact just a centroid, no matter what Bregman divergence you have. In fact, you can almost go backwards. You can say if you have the property that the centroid minimizes the sum of the distances, it must be a Bregman divergence. So what that means is that now you can run Lloyd's algorithm and you will get a sensible alternating optimization for any member of this class. And that will become important when you start talking about density estimation and EM in Gaussian mixture models or non-Gaussian mixture models. So this is one of those things where if you look at the algorithm, which is supposedly designed for one specific space, and you look at it carefully, you realize, and it took a while for people to realize this, only maybe 10, 15 years ago they realized this, that this generalizes. So the k-means algorithm is actually quite powerful. It captures something deeper, either in terms of an optimization or in terms of other classes of distances. Okay? All right. And again, this is not yet in the notes, and I want to put it in there. So it's going to be like the k-means plus stuff I talked about, how to do initialization better. That's going to be in the notes hopefully today. Might go off against that. But I have to get my act together in the next chapter. I'm not doing a preview. Okay. Let us now sort of review where we stand. I said this was kind of a good transition point, right? This is where sort of the first way of thinking about clusterings kind of ends. And so if you think about it, we have these three methods. We have K, center, median, and means. Thinking of now the problems here, and to some extent the algorithm we have. And so we can say, first of all, the cost function used is, I'm just going to draw them, is the radius of the cluster center, so it's basically some kind of radius. This is the sum of distances, and this is the sum of distances squared. You will find, and I've seen this before, people try to do k-means like clustering in a metric space. First off, does that make sense? So k-means like clustering, so they do exactly this and they put distance squared, but this is a metric space. So they replace this by d of x comma y squared. If you saw that, what would your reaction be? Does it make sense to you? So what I'm saying is I've seen papers where people say I want to do k-means like clustering in a metric space. So I set up this whole thing here, but wait, I can't write this anymore because it's not a metric. I don't have a norm, so I just replace this by d x comma ci. And I run the same algorithm as well.
My gut reaction is that it's effectively a vector of length 1, and that...
What's the vector of length 1? Vector of length 1?
Right.
Oh, what is it? You said there's a vector of length 1. Where's the vector?
Well, DXCI.
But that's a vector length k. There are k clusters.
Oh, you're right.
Otherwise, your representation changes every iteration. Well, the first problem you should ask yourself is, how are you going to do this? How are you going to, you can't do this thing. Why? Why not? Why can't I do this thing? Not that it would be wrong, I can't even do it. I just actually cannot implement this thing. Why not? So imagine your favorite metric space that's not Euclidean space. Everyone has a favorite. What's your favorite? You don't have a favorite metric space? Yeah, you've got to have a favorite metric space. Like think of a graph. Shortest path of the graph. That's my favorite metric space. That's not a Euclidean space. How do I do this? I have to somehow add the vertices and divide by size. How do I add vertices in the graph? Can you? Can anyone add vertices in the graph? What do you do? It's not a hard, it's not a trick question. Can you add vertices in the graph? Yes, no, maybe, sometimes. Would not catch up on it, but
When we define metric space, we are defining a distance metric.
yes.
We are not 2 points.
So you're saying you cannot do it?
No, I'm not able to.
You're walking up to the cliff, but you're not going to jump. Commit to your argument.
I don't know how to do
You are saying that you cannot do this.
Yeah.
I would say it's not defined.
It's not defined, see? Don't be so scared. There wasn't really a cliff there, it was just a mirror. You can't do this. I have not given you a way to add things. My rules of engagement only allow you to measure distances. So what these papers do then is say, oh, well, we can't do this, so we'll come up with some very clever scheme to replace this by some minimizer. At that point, what are they doing? They're doing k-median, but for some reason they have a square. And there's no earthly reason why they should do it. And I'm only pointing this out because you will often find it's easy to try and apply one algorithm in a place or a method in a place where it's not quite suited for. If you're going to do that, make sure that the assumptions underlying the method actually carry over. For Gremlin divergences, they do carry over. The things that we need are there. But if you don't have a metric, you can't actually apply this unless you do something clever. In which case you end up in k-median, which is the correct analogy of k-medians for this. Okay? Just a point. Okay, so you have these things here. You have this cost function. We know we can get a 2 approximation here. We know we can get a 3 plus 2 over p approximation here. And here we know we can get a 1 plus epsilon if we work very hard. If we use a simple algorithm, you can kind of get log n, or you can get 1 plus epsilon depending on situations. You can get some log. Okay? And this is the state of what we know. In terms of running time, how long does k-symmetric run? Okay, you want to tell me? I have n points in a metric space. I assume a distance evaluation costs me 1 unit of time, and I want to find k-centers. How long will it take? We've seen the simple algorithm for doing k-center, Gonzalez's algorithm. How long do you think it will take? Without being too clever. What's the right? We haven't talked about running time that much, but it's good to think about. So how long does each step take? Think of that. So the first step takes nothing. I pick a point. How long does it take to find the next point? N. Okay. How long does it take to find the third point? Again, you're not being very clever. What do you have to do to find the third point? You take every point in your set, and you compare it to these 2 points, right? So it takes 2 times n minus 1. Right? So if you're trying to look at the right time for k-center, something like it takes 1 plus n minus 1 plus 2 times n minus 2, right? Plus 3 times n minus 3, and so on. Right? Up to k. So it's sigma I times n minus I equal to let's see, 1, 2, and maybe just that first term. Okay. So what is this? This is basically plus sigma I times n minus I squared, I equal to 1 to k, which is equal to 1 plus n times something like k squared minus 3 within quotes. The all notation magic, just ignores the details, but it's basically k squared. So since n is bigger than k, we expect this to be the dominant term here. So it's something like nk squared. And again, I'm not trying to be too careful with the analysis here. But this at the symptotic level, this is roughly speaking correct. Take it something like nk squared. For k median, actually, it's a bit more mysterious. The running time depends heavily on this and the mode of convergence. So I'm just put it as some polynomial. For k means, again, we're not quite sure what the bound is. It's going to be some polynomial. If you use the appropriate initialization, you'll get some answer. And that's where things are. So of course, you could look at it and say, oh, k center is the most, the best method because I get a clear running time bound, I get this good answer. I should use it all the time. And of course, we've already talked about why that's not necessarily a good idea for other reasons. But now you have three things at your disposal. It's a good toolkit you have here. Right? You have a good set of tools now to think about things in a metric space, also in a metric space, but maybe more robust, and something better in the Euclidean space. I won't say better, but it's different in the Euclidean space. So we have tools now at disposal. And so what I want to do now is talk about what happens next. I have these tools, I can find a cluster. But let's look now at the problem that I promised we'd talk about, the problem of finding. As we've said before, we don't necessarily always know what the right value of k is. And if you think about how these algorithms work, they unfortunately have the value of k baked into the algorithm. Right? It's heavily baked in. Maybe not so much for k center, because you can stop early. But for the other two, you start off with k and you always keep k. And you keep searching. In k median, you start off with k centers, you keep swapping, but you always keep k. In k means, you start off with k centers, you might move things around, but you always keep k. You are committed to the choice you make. So if I don't know the value of k, as I've said, there are ways you can deal with this problem. You can say, run this algorithm for all values of k, and find where kind of the cost seems to dip very dramatically. Because maybe that's the point where I've really found the true number. And if you want a single answer, that's fine. But maybe you don't, right? Maybe you're trying to explore what happens in the data. So for example, suppose I have a data set that I have one big blob here, one big blob here, and one big blob here. And you'd run your choice of k, and you say, oh, okay, k equal to 3 seems like the right answer for these 3 blobs. But now you go look into these blobs a little more closely. You're exploring the data after all, right? And what you see is that inside each of these blobs, right, is really this. So if you zoom in enough, now you think, well, maybe I actually have 9 clusters and not 3. And it's not obvious to me which is the right answer. I can't say for sure that 3 is the right answer. I can't say for sure that 9 is the right answer. It depends. And in an exploratory setting where clustering is most often used, you don't want to have to force your hand early on. You want to be able to understand the range of possibilities before you commit to looking for a particular condition. And so the thing we're going to look at now, which is hierarchical clustering, is a way to get there. One easy sort of fix, if you say, well, no, I don't want to look at a single cluster, I want to look at all of them, I say, okay, fine. I will just cluster it for all that is okay and give you all the answers. You surely can't complain with that. So let's say I take 6 points, put them on the line. These are not very well clustered, but nevertheless, this is our data. And of course, you should think of this as being in some 100-dimensional space. You don't actually know this is what's happening. So I say, okay, I'm going to cluster these into 2 clusters. I might, do something like this. say, okay, I want to cluster them into 3 clusters. So I might do something like this. Then I might say, well, actually, what I really wanted was 4 clusters. And I want to look at that. Now it gets a little bit tricky when there's not. The right answer is maybe I do something like this. Oh, sorry. Or maybe this is not even the best answer. Maybe you do something like 2, 2, 1, and I do 5. So you could give me this collection of clusterings, and I could scan through them, try to understand what's going on. And one annoying property with this, and this is both a problem kind of visual fidelity as well as just interpretation, is that my answers don't stay consistent. 2 points that used to be in different clusters get in the same cluster, which is fine. But now they get separated. So they start off separately, and then suddenly they get okay, sorry. So let's look at these 2 points. They start off in the same clusters, and they get split up into different clusters. These 2 points start off in different clusters, and they go in the same cluster. What we'd like is something where it says, okay, I start off with everyone all by themselves. And as I decrease the number of clusters, things tend to collapse into a blob, like in one blob at the end. But once I put 2 things in a blob, I would prefer to keep them together because I made this choice. And I don't want to, at least in my answer, I don't want to have things kind of bouncing around. Because it's hard to interpret. If I look at the answer for 2 and the answer things have changed crazily, it's hard to understand what's going on. It's very unstable. So the idea of a hierarchical clustering, hence the name hierarchical, is saying I want to generate a family of clusterings that are good but have this nice property. Namely that as I increase the number of clusters, or as I increase the number of clusters, things just split. If I decrease the number of clusters, things just merge. I don't have mergers and splits happening. Okay, that's the goal. We want to find a clustering or a family of clusterings that has this nice property. So if you will indulge me a little bit of philosophy, the underlying philosophy of a hierarchical clustering is actually quite deep. It's deeper than you might think it is. Because what it's saying is that we don't understand the structure of the data from a single snapshot. What we're trying to look at is kind of like a time-lapse movie over the data. And it is the entire movie that gives us some structure to what's going on, not any particular snapshot. Right? So if I have this clustering and this clustering, they're all different clusterings, and if I look at each one of them, they tell me something. But what is more interesting to me is how they relate to each other. Okay? In other words, the messages in the gaps, not in the points. The transitions are what are important here. And this idea has been more recently, the last 5-10 years or so, being developed far more rigorously and informally using topological methods. And if time permits, towards the end of the semester, I might either talk about it or have one of our local experts who lives up here in Ski. She might come and talk about topological data analysis and the idea of using topology to understand these gaps. But hierarchical clustering is your first sign that there is another way of thinking about the structure in data. Not just a single clustering, but as an ensemble that together tell a story. Okay? So keep that in mind. And that's one of the reasons why it's so popular. Because it's giving you much more information about the data than just the partition. And it recognizes that sometimes that's what you want. You want to partition data, yes, but you want more. Okay. Yeah. But you don't, that's the thing, you don't do that. You build a family of clusters. You can extract a K clustering from it, and I'll show you how to do that. But that's not your goal is to build a much more a universe.
Yeah, all the data points, see that this is one cluster, we take it down into 2, then we take it.
So I'm going to tell you how to do that. Yeah, okay? So the first thing I want to do is get into any algorithms. What I'd like to tell you is what is the output, right? So when I do a regular clustering, the output is a partition. What's the output here? The output here is a tree, or tree. And the tree kind of looks like this. It's a tree, of course, and it has, it's a rooted tree, so there's a root, and there are nodes going down. Right? And I'm drawing this as a binary tree, but there's no particular reason to be doing that. It could be, more complicated. This binary makes it simple. At the bottom, you have leaves. Okay? You should think of the leaf. Every node of the tree is going to be associated with some subset of the input. So if I start writing down properties, right? It's a very axiomatic way of saying this, right? So, hierarchical clustering is a tree with a root. So and there's a function S which maps vertices of the tree to subsets of the input. Like this complicated way of saying map it to a subset, such that so that means for every vertex in the tree, there is some subset of the input that is associated with it. Okay? And if UV is a parent-child relationship, then we want SU to contain SV. So the sets get smaller as you go down any point. Okay? Furthermore, what we want is that if U has children B1 to Bk, then SU, the set associated with U, has been partitioned into the sets associated with the V1. So it's equal to the union of S of V. And I'll put a dot here say it's a partition, so there are no overlaps. Make sense? So the top is the entire set. So that's X. So they go down by this rule. I have to find subsets. By this rule, they split. So you split it into, say, I don't know, some X1 and X2. And you split it again, At the bottom, you just have the input pointing units. X1, this would be X5, X3, X2, X6, X4, so on. So the output of the hierarchical clustering algorithm is this tree. It's not a partition. Yes?
So the example that you threw out there, though, would not qualify because that center 2 would come back in together, so it's not a tree.
Exactly. Okay. If you want to get all technical about this, the space of partitions of a set of objects forms what is called a lattice. Okay, because that's a directed graph. It's got like diagonals and stuff. We are saying no, we don't want diagonals. We just want a tree. So you're restricting the space you're willing to look at because of these other reasons I mentioned, for persistence problem. Okay, so that's the output. It's no longer a single partition, but it's a whole collection of these. And so here, this is already, as you can see, it's telling you a story, right? It's saying, there's some affinity now between these points because they get grouped in a certain bunch and those groups go up. At the top, they're all the same, but they split up in different ways. You could imagine different ways of splitting them up, giving you different answers for your data. Okay. And if I wanted an actual, I want a clustering, I don't want all this tree nonsense. It's very easy to get what we want. Right? What could you do? For example, you could say, fine, I'll just take a particular level of the tree and cut below that. What's going to happen? What this is basically saying is that these now become my leaves, and this is one subset. That's another subset. They partition the input, so I have a clustering, a 2 clustering in this case. I could partition it here, and I would get a 4 clustering. I could also get crazier though. I don't have to do it this way. For example, let me draw this. Now this clustering consists of this set. Did I lose correct? No, this is wrong. This is not going to give me what I want. Sorry. Let's just keep it simple. Okay. So I get this set, I get this set, and I get this set. They're not on the same level. But notice that these two form a partition of this set, so they account for all the elements here. This and this form a partition of this. Actually, this 3 clustering is in fact a clustering of the data. but it's sort of sub-refined adaptive, which is also nice if you want to kind of zoom into certain areas but not others. In this case, I zoomed in maybe just to this cluster, but not the other two. So now you can see that you have a whole plethora of clustering, factual partitions you can produce from this tree. So this tree sort of, it contains universes inside it, right? So it's much more than just a single snapshot. And that's what I mean by it has more information. It's giving you a story, and you can construct different snapshots from it. This is particularly popular in the world of biology, especially when doing evolutionary tree analysis. And in fact, the folks there have coined a very nice visualization called a dendrogram that allows you to visualize these things. I will get to that. We'll see if I get into it, but I'll talk about that. It relates to certain things. So any questions so far about hierarchical string? Does that make sense? Yeah.
Does it have to be binary?
No.
Can you do whatever?
The binary is convenient because you can think of that as a single set being split. But you could split multiple things at the same time. So it's not really, it doesn't make sense. Any questions? Okay. So having defined the idea of hierarchical clustering, having defined the desired output and the properties of the output, we're kind of now ready to actually say, okay, can I produce an algorithm for producing this? So in the grand tradition of clustering algorithms, we will omit to actually define a cost function. This was the only case we actually had a nice cost function. We'll just define the algorithm first and try to retroactively fit a cost function onto it. But there are basically two ways you can think about designing an algorithm for doing hierarchical clustering. And I'm wondering if you have any thoughts on it. So the two high-level approaches. First, very vague high-level intuition for how you might go about it. You don't need a complete specification. I just want an idea. Yeah.
This intuition.
Yes.
What maximum?
So what does that mean?
Start with the maximum number of clusters.
Like all the input points. Yeah.
And then gradually build up.
Gradually build up. Okay, very good. That's one way of doing it. What's the other way? Okay, and then? You do two groups, and then what do you do?
And then use another attribute to break up the
So you recurse. Okay, good.
Decision tree.
Huh?
Like decision tree.
Like a decision tree? Very good. So in other words, you either go from bottom up, what you say, or you go top down. And that's basically it. There are two approaches, and you go either bottom up or top down. Okay, so since we're doing a top-down description of our algorithms for top-down clustering, so let's take the top-down approach. Okay, so let me first, this is my hierarchical clustering algorithms. Okay, so we have top-down, then we have bottom-up. So let's go further down here. So it turns out that, and this is again something we like to say, we like to do in computer science, but we like to be lazy. We like to reuse what we've had before. I have all these nice tools for doing clustering. Can I use them to do top-down clustering? How much? Could they help me somehow build this top-down clustering? Top-down tree. Sorry? Yeah, of course you don't have to pick two. No, you're thinking, okay, you're on the right track, but you're thinking very low level. I'm saying, I give you some black box that will give you a K cluster. That's all it gives you. You don't know what it's doing because you're running K inside, you're doing it. So it's a black box. You give it data, out pops a cluster. Can you use that black box to solve this? Just try to recurse. So if you have any kind of what people often call flat clustering algorithms, right, as opposed to hierarchical, just run it. So take my input. So run some K clustering algorithm on X, which gives me cluster C1 to Ck, right? Recurs on Ci. That's all we know. So the first step will give me this, the next step will give me these, and so on. Now, there is this again annoying thing about what K do I pick now. But since I'm just trying to build a hierarchy, I can just pick two. care that much about what number of things I do. So I'll just say do 2 clusters. Yes.
Can the key change between
Sure, if you want to. Yeah, absolutely. Right. So this is really a template, not so much a single algorithm, but a template for it. You could imagine being more clever about choosing K, you see something happening. And the running time of this, actually, if you think about it, it seems like you're doing a lot of work, but remember, you're splitting it every step. So if you're willing to assume, this is a big assumption, that things split more or less evenly, then the recurrence for this will be something like T of n, the running time for n points is equal to, let's say the running time for this is G of n, it will be something like K times G of n over K, assuming an equal balance, plus G of n. For those of you who were in algorithm last semester or before, you know this will basically be G of n. For any G of n that's super linear, which these things tend to be, this is volume thing. So it'll be some constant time G. If it's not even, then of course all bets are off. Then things get crazy. Okay, so if things are roughly balanced, this will take not much more time than running this once. And you get an factor. It's also global, so it's kind of nice. But it does require you to have this kind of heavyweight platform. We have access to it in the platform. And so this is all I'm actually going to say about top-down methods. Because for some reason, and I'm not quite sure, the bottom-up methods are way more powerful. And you'll see why they're very easy. So maybe that's why. But that's pretty much all you need to know about how to do top-down hierarchical clustering. It's also called divisive clustering to make it run. So that's another name. Divisive. You will find that there are other ways to split. You could run a K clustering, you could do some other more clever things. There's no reason you have to run a clustering algorithm here. You could be more clever about your function. That's up to you. As long as there's some black box to split, then you can do this. So that's all you do. But the thing that I will spend a bit more time on, just because historically that's been far more interesting to study far more extensively, is what is called the bottom-up relation. And there are many ways of doing this. We'll just go to the most basic thing. This is also called agglomerative clustering, because you're merging things together. So if you're doing hierarchical clustering, that's agglomerative. You often call it hierarchical agglomerative clustering. You call it hack, which makes you sound like a very bad cough. And that's what you do. So if you see the literature, hack is what you do. How would you design? So you kind of alluded to it, how you do it, but that's okay. So the idea is somehow you start on the bottom and you merge things together. So that's what do you think is the right thing to do? Intuitively, what's the right strategy? So I have a bunch of points, and I want to build this hierarchy. Bottom up. Watch. Yeah.
We approach this some of the other problems in marketing.
Sure.
Segmentation. All the people.
Yeah.
All the points that you have. Then you create some clusters. Each step you treat those clusters as points.
Yes. Correct. And you recurse all of this. How do you find that first cluster?
Well, that's a subjective thing where you can have all the points you think that's the widest net that you can cover.
Yes.
Or if you have some intuition about the lowest possible cluster that already exists there.
So let's say I don't know anything.
Then you can cast them up.
Then what do I do? So assume that, assume I have some notion of distance from this thing. Let's say I have a metric. I haven't said that, but let's say I have a metric. What can I do? Why closest? So you want, well, not including, I have a metric. But you want closest because you're saying, right. So in other words, what I'm going to think about is that if I have all my points laid out, and think of this movie, right? I'm zoomed in really close to a point. If I start backing out a little bit, what's the first thing I'm going to see? The point that's closest. So imagine I have cameras at every single point, and they're all zooming out at the same speed. Who's going to fire off an alarm first? which one is going to fire off alarm? So think about it. I have cameras at every point. Okay? And I start zooming out. So I start seeing bigger and bigger regions around the point. But they're all going at the same speed. When will two cameras crash into each other? Or start seeing explosives? Sorry? Yes, but in particular, which 2 points will fire off? Yeah.
The two closest points out of all.
Two closest points, yeah. I'm not asking hard questions here. That's what the two closest points will react first, right? So I say, oh, okay, these two form a cluster. Okay. Okay, I keep zooming. My movie's still going on. Right? What happens next? What's going to fire off next? The next closest pair. Yes?
But so after that first cohesion, do you redefine the cameras, if you will, if we're using that terminology to
A single camera?
Yeah.
That's a good question. What should we do? What do you think we should do? I'm open to suggestions. So this goes back to what you were saying about somebody blob them at the scene. So what do I do? So I connected them up. I want to keep that information because I want a hierarchy. So I want to keep them together somewhere, treat them the same way. How should I do it? I could average them. So then you want to say replace them by the centroid. Okay? I'm in a metric, sorry. I'm in a metric space right now. When we get to Euclidean things, you can, but now I can't. No, I'm sorry, I can't average. I don't have that capability.
So you can just define something to be the smallest distance to any member within its collection.
Yeah, we've seen this before, haven't we? With case centers.
Right.
So say that the distance from a point to this new blob is the distance to the closest one. Okay? So in other words, we knew how to define distances between points. Now we're going to define the distance from a point to the set as before as the min. Okay? Okay, our blobs keep going. Now we get another blob. Maybe these two, maybe nothing happens here. Maybe we connect them up. And then maybe, I don't know, maybe this becomes a big blob right here. Then this big becomes a big blob right here. So let's number them. So let's say it goes with 1, 2, 3, 4, 5, 6. So if you look at our tree, what's going to happen is what? So 3 and 4 are going to merge first. In this particular movie, 1 and 2 are going to merge next. Then I said 5 merges with 3 and 4. So that comes here. And then 6 merges with 3, 4, 5. So that comes up here. And then finally these two sets collapse. It satisfies all the properties that I said I should show. Right? This particular flavor of hack, using this way to define the connectivity, to define the closeness, is called single link. The reason it's called single link is because you're saying you just need one connection to the cluster to measure the distance. And this is by far the most popular flavor or variant of hack. For those of you who took an algorithms class either this year or last year or some other year, this should remind you of something. If it doesn't remind you of something, I have to go back and change it. This should remind you of something that has nothing to do with clustering, but has something to do with graphs. Any thoughts? I'm taking an edge and I'm collapsing things. I find the next closest edge and I collapse them. Yes? You were seeing it? From the tip of your tongue?
Yeah.
It's coming, it's coming. Anyone? Not a flow, something else. Should I stare at my TA from last class? Actually, but 2 of my TAs from last time. Once you see it, it'll be obvious. But till you see it, you might not see it. That's one of those annoying things about this. So, minimum spanning trees. How does Kruskal's algorithm with spanning trees work? You take your set of points. So the minimum spanning tree problem, for those who are not familiar, is given a graph with edges, with weights. Find a subgraph, which is a tree. Find a tree that connects up all the points of minimum total cost, where the cost is measured by the sum of the weights on the edges. And the way one of the algorithms for this problem works is take the pair of vertices that are closest together, long. Take the next pair that's closest together and measure it this way, and then do it. You can think of K clustering as basically running Kruskal's algorithm and stopping when you have K clusters. In the beginning of N clusters, you merge things up. At some point, you stop when you have K, that's a K clustering algorithm. And if you run all the way top, you get basically a minimum spanning tree. Okay. So single link hack is an MST. Okay. So in particular, this minimizes the sum of these distances, the sum of all the distances in the tree. Right, so in this case, 5 was connected to 4, 6 was connected to 5. So the tree you get here will be, let's say, move 2 connections to 3. The tree you get here is 1, 2, 3, 4. It didn't be a path, I'm not sure what. This is the tree you get. The cost of the edge of the tree is what you're minimizing the signal. This may not be the best clustering objective, but this is something that you know you optimize. Okay? Now there is no reason, really, that you have to pick this. Right? This is being very optimistic. And in the sort of grand tradition of how we think about these things, stop right there. Tell me when this algorithm will fail. Or tell me, when this algorithm, not this problem, but when this algorithm will fail. The one you just described. And when I say fail, I mean that it will give you an answer that is clearly not right by some visual view, like you can see today. So I said every clustering algorithm is flawed, right? What's the flaw? When 3 points are equidistant to each other, so let's run the algorithm. When I have 3 points, they are equidistant to each other. So what's going to happen first? So I choose these 2. Okay, what's the problem? I did. So why is it a bad thing? Right, but it's not wrong, right? I mean, there may be other choices, but this is not a wrong choice. It's just not unique.
Calculating the minimum distance for 2 blocks might result in bad answer.
Why? You're on the right track. Could you explain more? Yeah?
Or I was just thinking maybe the 2 blobs exceeds like the diameter of the blob, all of the stuff that you're participating in.
Exceeds? Why exceeds? The minimum should be that's actually a good thing. Right? That the cluster is small, the minimum, that's a good thing.
Right.
If that's in fact the shortest distance you have. That
Right.
means so I mean, that's fine. At some level, your clusters are all of them have blob anyway. But again, you're both are kind of nibbling around the right idea. So retreat a little bit. It has to do with blobs. It has to do with the fact that I'm looking at a single measurement between 2 blobs. But why?
You have to make some assumptions about the center of the blocks from here.
You can construct any input you want. I'm just saying, given this algorithm, give me an input that will kind of take it out. But here's one thing that's kind of well known as a problem with single linkage. And again, it goes back to the blob edge. Suppose I have a set of points with a line. And they kind of look like this. So there's a point at 1, point at 2. There's a point a little bit beyond 3. There's a point a little bit more beyond 4. A little bit more beyond 5, and so on like that. So it's like I want the minimum distance, right? I'm going to pick these two first. But now what's closest? This one is closest next. So I'm going to fix this. 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 What you end up with is basically no structure at all. You end up with a hierarchical clustering that's basically, 1, 2, 3, 4, 5, 6, 7. There's really nothing in it. What you would like is something that says, no, I want, this piece here, this piece here, this piece here. In other words, single link clustering aggressively follows prompts to try and put things in a single cluster. Here it's a bad thing. But now there's another case where it's actually a very good thing. And this goes back to where things like k-means will fail. And if you read the blog post I posted, you know the answer to this question already. So there's also a test to see who really knows. Give me an example where k-means is going to fail horribly, and this will work. In fact, any of those algorithms are going to fail horribly, and this will work. I don't know if you read the post or not, but yes. If you have two clusters, right, and one cluster looks like this on the outside, right, and another one looks like this on the inside. This is a terrible case for all these distance-based methods, because they're going to partition things into blobs that are separate from each other. They really have no way of dealing with this. I mean, there's a trick to, there's a thing called lifting map, and I won't get into that, but as such, if this is what your data looks like, and you don't know what it looks like, any of those three methods will fail horribly. They'll try to basically cut things across and just make no sense. But hack will not fail. Why will hack not fail? I mean, it's exactly for this thread following property. If you seed hack and you pick points that are here, and then you pick points that are here, this is going to follow this entire structure around and pull it all in before it ever touches that. That's going to pull that entire structure around and get it in, because locally it looks close before it collapses these things together. So because single link follows local links very carefully, it can find clusters that are contiguous but not in a kind of spherical way. Things like k-means in particular and other methods are trying to find these balls that you can carve out of space. This is trying to find things that are little snakes that are connected. Right? So for example, you can imagine another set that looks like this, and it looks like this. Again, hack should do well on this. Those methods will not. So this goes back to the point I was raising earlier, right? All clustering methods are bad except in the long term. And so you have to understand what kind of patterns are going to be found by these methods based on how they expect to look for data. If you look at this cost function, it's not obvious that it will find balls. But if you start playing with what it's doing when it runs it itself, you will see this is what it's going to try and find. It's trying to find bounded variance blobs. Whereas this is following trails. So if you have some basic sense, okay, here's what I might be looking for in my data, and it might, you really should be using that. You're going to get horrible answers. And if you use this, you would get a good answer. So conversely, if you ran these different methods, and one gave you a good answer, one gave you not, that's telling you what kind of structures might be there or not. Okay? So we'll talk more about single link hack and other methods like this. There are other ways of combining things together into one group. Next lecture. But I want you to go away with for a couple of ideas from here. First of all, that hierarchical clustering is a very different way of thinking about representing your data. It contains the idea of a clustering within it, but it also contains much more, a whole story. And secondly, that hack is the first example of something where you get very radically different cluster shapes than you would get with any of those distance-based methods. They are different, right? Robustness and things like that do make a difference there. But the difference between them and this is much more than the internal difference between each other. Again, if you build a hierarchy, they're kind of here, and hack is somewhere here. Okay? And as we go on, we'll see other kinds of clustering methods that give you, again, very different ways of thinking about it. Okay? All right, so I think we'll adjourn for now. See you all next week. Don't forget the assignment is due